If you return to our tutorial, we now need to orthogonalize ATA. So we need to make an orthogonal matrix. Either way, there are a few algorithms with which we can orthogonalize or even orthonormalize a matrix, this matrix in particular, and that is called the Gram-Schmidt algorithm. So let me show you the Gram-Schmidt algorithm. Let me add one thing before I return here. So this is how you denote the dot product. This is one way to do it, this dot here. Another way to denote it is like so, to use vertical brackets. So either this one or to do this. Two, if you see this notation, that's the same thing as that. Both of these are, dot product. You can call this dot product because there's a dot in here. You can call this inner product because, well, they're inside the brackets. If I come here, you will see that in other examples, they use the brackets. Anyway, let's see what's going on in here. Say you have a basis. Basis, we set basis has two conditions. First of all, so this is a set. This is the basis. This is a set. It has vectors, v1, v2, vn. All three vectors must span the subspace. What's the subspace? Rn. So let's say we're talking about a three-dimensional space. So we need 3 points, x, y, z. Each vector must have x, y, z. You can't have one that is 2-dimension, another one that's 4 dimensions. All three must be of the same dimension. That's condition number 1. Condition number 2, they must be independent. What does it mean for two vectors to be independent? It means that when you take the linear combination, and the linear combination is this. So let's say you have two vectors, and you have two scalars. Multiply this scalar by that vector, multiply that scalar by that vector, add the product, it will be equal to 0. We saw this in another example. We saw this in the last session. So that's what a basis is. Okay? For now, just imagine it's just a matrix. If we were to put these 3 columns inside, if we were to take the components of these vectors inside angle brackets, it will be a matrix. So for now, consider this to be a matrix. Column 1, column 2, column 3. How do we orthogonalize? You define a new variable or new vector w sub 1. And that is just identical to v sub 1 with components, or with points if you like, 1, 1, 0. Then you will use the first vector w sub 1 to create a new vector w sub 2. How do you create w sub 2? You take vector 2 and subtract it from this ratio. So you have the dot product of v2 and the first vector over the dot product of the first vector. I mean, exactly as you see it here. This will become the first vector of the new matrix. This will become the new vector of the second matrix. This, the new vector of the third matrix. So you must multiply the scalar value by the components of this third vector. If you do this multiplication, if you do the scalar product, you'll get 0. So in total, we will get a new matrix. So the original matrix was 1, 1, 0, 1, 2, 0, 0, 1, 2. This new matrix will be, this will be its first column. This will be its second column. This will be its third column. Now, this is orthogonalization, actually. So these are the vectors of the orthogonal matrix. These are the vectors after it has been normalized. If we take the square root of 2 over 2, so that's 2 over. You can see it is 0.7. What I'm trying to say is none of these components, the square root over 2, any of these components are above 1. So when we normalize a vector, none of the points in that vector exceed 1. They will be between 0 and 1. If the notation is a little too overwhelming, and it kind of is, let me simplify it by taking you back to Colab. Okay. So let's actually use this as an example.